I'll get started. Hello, everybody. Thank you for coming to Cleveland Big Data. I know folks are still going to roll in, but we'll get started. March 21st, 2022, virtual style. Hopefully, we can get back to at least doing the hybrids. I know Cal and I were talking about that. I'd like to try something for March. I'm sorry, for May, even if it's small, to start getting in the habit. I know there's a lot of folks who miss the networking, and yeah, so we'll try something in May and see what happens. So we've got a great agenda today. We've got Data with machine learning model explainability, Influx Data with running arbitrary compute workloads in a multi-tenant environment, and a talk on Arista, from Arista on next generation network packet broker, easy for me to say, architected for pervasive organization-wide visibility and security. So with the announcements, and again, I keep reminding folks for the member approval process. So there's I do have to do that. I usually turn them around within a day because I had some bad drive-by spam with Meetup about 12 to 18 months ago. So I've been approving just about everybody, but for all the new members, that's why there's an approval process. And again, the most important one is the friend of the show. So if you are a friend of the show, if you do a presentation for Cleveland Big Data, you become a friend of the show. That's a lifetime honorific. You can put it on business cards. You cannot, however, gift it to your children or sell it on the open market. But it is yours for life once you do a talk for Cleveland Big Data. And like I said before, and I don't believe you can also turn it into a non-fungible token either. This is something that it doesn't work that way. And again, let's try a hybrid meetup in May. There's a blog I was talking about before I started recording called Making Bad Decisions. It's my latest blog. I think you might like it. It's on it's about a real life incident with installing whiteboards in Explorers' first office, and it's a great mix for a great case study in organizational dynamics and decision making. So read that when you get a chance. So from recruiting shout outs, so Progressive's got a couple of positions, data architects and data science positions. PNC Bank has 2 senior business analysts in their data center of excellence. And I put the dash in there because if you didn't, it would read data center of excellence. And I think what the roles are is the data center of excellence. Does that make sense? The dash matters. So it's in their data group, and there's the links. There's a few more. There's another Cleveland-based data scientist for here's the link, and then there's a few other positions from Bell Falls Search, and Ride Beep also pinged me today, and Matthew asked me to say if anyone's interested in Ride Beep, just email them directly. They've got a listing of positions there, and but he did ask me to stress to please just have folks email if they were interested in Ride Beep. And as always, Linux Foundation. I literally could not do this without them because we're using their Zoom. And also thanks to John and the Linux Foundation for posting the recording of this meetup to the Linux Foundation YouTube account. So again, thank you so much. It makes the virtual meetings possible. And with that, let's go on to the first presentation. So let's turn it over to Data. And I'm going to stop sharing. And you guys take it away. So remember, it's a 20-minute slot. It's your call on whether you want to address questions during or wait to the end. So just let folks know if you want to address questions during from the chat, you can. Otherwise, you can just talk all the way through. Cool, go for it whenever you're ready.
Great. Excellent. So thank you guys for coming. Today, we're going to talk to you about explainable AI in the realm of healthcare, specifically in hospital readmissions. So I'm Marilise Yoon. I'm an associate data scientist consultant with Data. Today I have Nikki, who's also an associate data scientist consultant, and Nicholas Stabellini, who is a MD PhD fellow at UH and Case Western. So I'm going to turn it over to Nick to talk a little bit about the background of our project, and then we'll get into the explainable AI part of it. So Nick.
Thank you, Marilis. Hello, it's a pleasure to be here today. And my goal is to explain to you why readmissions matter in the context of the healthcare and why this project is so important. So first, talking about general readmissions, as you can see in this infographic, preventable readmissions costs about $17 billion to Medicare, and the patient care costs double due to just one readmission. Further, 1 in 5 patients are readmitted in 30 days. This analysis is based solely on the Medicare population, but it can be extrapolated for the entire health system. And one of the suggestions to solve this problem, as you can see on your right in the number 4, is the use of prediction software. That's exactly what we are trying to do here. So going to the next slide. When we look specific to cancer patients, this situation is even more complex. These patients are in higher risk for readmissions because, as you can imagine, they have weakened immune systems and are in constant use of medications. They also mean higher costs for the system. And the current readmissions models are usually not cancer specific, or those who are just work for one type of cancer or are very hard to implement in the clinical practice. So for that reason, our aim is to create a tool to predict and prevent third-day unplanned readmission for general cancer patients, and that can be explainable and implemented in the clinical practice. Next slide, please. So the specific objectives of this project are to, number 1, create a model that's based solely on cancer patient data. Number 2, improve recall over current models. And number 3, prioritize interpretability without sacrificing any predictive power. And giving to you a quick background about our project and idea, it started in Cleveland Clinic and moved with us to university hospitals. And we have the expectation to have, in addition to a scientific publication, a tool like an app or integration to the electronic medical record, where doctors insert the patient's information and receive back a readmission history for this patient, so they can elaborate a better follow-up and prevent this event, the readmission. We also have a partnership with an institution from another country to validate our model and make it more reliable. So next slide. And the preliminary data used to reach our objectives contain more than 14,000 patients, with 11% of them experimenting the outcome at third-day unplanned readmission. And the features used were demographic information, cancer type, admission information, vital signs, lab values, medications, and previous visits to the emergency department. And now it's time to Marilis go forward and explain how we performed this amazing project.
All right, great, thank you, Nick. So explainable AI is something that's going to help us improve the model, but without sacrificing the interpretation. So, coefficient-based methods like logistic regression, they're very interpretable, but they don't always produce like the best results. You don't always get the best accuracy, precision, recall, whatever metric that you feel is the most valid in your use case. But complex models, they can produce better results, but they aren't explainable. We care about explainability because, like Nick said, this is eventually going to get into the hands of doctors who need to explain, why they're recommending something or something else for their patient based off of their likelihood to be readmitted. So, we're trying to get around the problem of the black box, where you just input features and you come out with a prediction. You don't know what's happening in that box, but for some reason it's predicting something. So explainable AI helps us get around that and helps us understand and trust the results that are coming out. It helps us check for biases, like if we don't want to consider, gender, but maybe the model is making that a very important variable. It can help us satisfy legal requirements. There's not too much regulation in the space in the US quite yet, but it's probably coming down in the next 5-10 years or so. And this can also help us monitor and validate models. It helps us, make sure that the results that we were getting, a day ago or a month ago are still the results that we're seeing, as the model gets put into production. So what we're doing for explainable AI specifically is we're looking at SHAP values. So SHAP is a game theoretic approach to explainable AI. And what this means is it's kind of distributing the payout of models, the prediction among the different features. Effectively, what it's doing is calculating the average marginal contribution using all possible combinations of features. This is not, and I'm going to probably emphasize this multiple times in the presentation, it is not the difference in predicted value when you include or remove the feature. It is not a coefficient. It shouldn't be interpreted the same way, but it is similar enough that it can tell us information about the model. So our specific implementation that we're using is called tree SHAP, but it's an algorithm that's been optimized for tree ensembles, but doesn't require the same compute time. So we have kind of a basic example to demonstrate how this works. So the MT cars data set, I think that's like built into every statistics program ever, but it is looking at, for this one, whether a car is manual or automatic, and we're predicting manual based off of the fuel efficiency, miles per gallon, cylinders, the number of cylinders, and the displacement of the engine. So we get out a nice set of coefficients here. We know exactly that every 1 unit increase in displacement decreases the log odds of being a manual car by 0.02. Now, logistic regression doesn't always have the best results, though. So we want to run like an XGBoost model on this. XGBoost models are not interpretable in this sense, but if we add SHAP in, then we can start to interpret. This is an example of what SHAP looks like when we're plotting it out. So we have on the left here on the SHAP plot the 3 features that we're taking into account: displacement, miles per gallon, and number of cylinders. Each point represents an individual observation and the SHAP associated with that observation. And then the color represents the feature value. So in this case, we can see that for displacement, that is the most important feature that the model is identifying. And we can see that high values, the purple values, are associated with a negative effect on the prediction. So, higher displacement has it decreases the probability of being a manual car, just like the coefficient in the logistic regression. You can see the opposite for the miles per gallon. So higher values of that is associated with a higher effect, a positive effect on the regression and the results. So there's a number of advantages and disadvantages to using SHAP. I'll just go over a couple of them briefly, but SHAP values in general, it is in the game theoretic sense, they fairly distribute the gains from the prediction to all the different features. And it's a very solid theory that would, hypothetically hold up in court if you were asking me to attribute like different parts of this to different features. On the disadvantages side, if you're doing like a full SHAP analysis, this is going to run in, 2 to the number of features time, which is, as you get higher and higher number of features, that's going to run an incredibly long downtime. So the implementation we're using runs in polynomial time. So that's better, but it still increases significantly when you have more features and different levels of your trees that you're employing. Another issue is that this is very easy to misinterpret. If you are treating these like coefficients, that is not the ideal way of doing it. You want to make sure that you are saying, like, given this set of feature values, the SHAP is the contribution of a feature value to the difference between the actual prediction and the mean prediction. So it's similar, but not the same. So let's talk about the model itself. So we used an XGBoost classifier. We are oversampling the minority class, the unplanned readmissions. We did some hyperparameter tuning with random search, five-fold cross-validation, and we tuned to recall as our metric. So for our results, these are preliminary results based off of the data that we have available now. One of the big issues in this project has been making sure that we can get high quality data from the available data sets at UH. We wanted to make sure that we are including everything that's relevant and being able to backfill all the missing data. So currently we're working off a preliminary data set. As we iterate on this project and develop it further out, we're going to be including more of that missing data or backfilling that missing data. We're going to be including other variables like the social determinants of health data. They'll be very relevant in this case. But currently our recall is sitting around 0.58, precision is only sitting around about 0.19, 0.2. So we're focusing on recall again because we think it's more important to identify the cases where they should be getting more help and then they aren't getting more help. So we're valuing those false negatives more than we're valuing those false positives. Now, what does this look like when we turn it into, run it through the SHAP analysis? So we have, here are the 10 most important features that we've identified in the model. The most important feature is whether or not someone had an elective admission. So if they are having an elective admission, we can see that that is decreasing your probability of a unplanned 30-day readmission. On the other side, if you are not being discharged to your home or hospice or like home health care, if you're getting this other discharge, then that is increasing your probability of being readmitted. So the values themselves, like I said before, are your SHAP values. These are your average marginal contributions over all the observations. Each data point is an individual observation. So some of these are well divided between the two. We have a sharp contrast. Some of them are less well divided. There's a significant amount of overlap in color for like minimum sodium. But let's show you the local analysis of this next. So one of the great things about SHAP is that we get this global analysis, but we also get a local analysis. So for each patient, we can go in and look and see this patient was predicted as, yes, they're probably going to have a readmission, or no, they're probably not going to have a readmission, and this is the reason why. So for this particular patient, we are predicting a readmission here, but we can go and see that the reason for that is that they have an other discharge. This was not an elective admission. They have a substantial number of medications that they're taking, that they're a smoker. So all of these factors contribute to this prediction, and we get out our final prediction. I think this is log odds here. Now compare that to patient 2, where we have an overall a negative prediction. So we're predicting that they're not likely to be readmitted. So this is not another discharge. This is so that's pushing it towards the negative side. They have an elective admission, which is pushing it towards positive. But other factors like the minimum sodium level and the low number of medications they're taking each year are pushing them overall towards the negative side of things. So I just wanted to show off a little bit of the code that went into this. We are using 3 main packages here, and we're doing this in R. So we're using MLR3 for our actual modeling itself, going through all of the different hyperparameter tuning steps. But then we're pulling it out and we're doing the global analysis in a package called SHAP for XGBoost. And then the local analysis that is done in another package called TreeShap. Now they're both using the same underlying algorithm, but they seem to be, like the first one seems to be better at that global approach in terms of like their plotting capabilities, and TreeShap seems to be better at the the local approach. And one kind of tricky thing that I'd like to point out is on their line 114, it's a little tricky finding where the model exists if you're using MLR3. Now, this isn't an issue if you're using like the straight up XGBoost package, but if you're embedding your model in a series of objects, then it can be tricky to find it. So I'm going to end the talk here. We'll have some time for questions. But I just want to say thank you very much for coming to our our little presentation here. We have a list of resources if you want to learn more about SHAP and explainable AI in general. So I'll leave this up for a little bit that you can look through it. Thank you all. Are there any questions?
I've got a starter one I can throw out. This is Doug. So why R as opposed to any other language? Can you talk to that?
Sure. R was installed on the laptops that UH gave us.
Done and done.
So yeah, there's a lot of great packages in Python for this as well. So I think we have the last one on the list here under SHAP packages. That's the particular Python package for this. You can do SHAP analysis or explainable AI in whatever language that you're working with. But we just had R installed, so that's what we used.
Did I follow correctly that you have to, sorry, this is Adam Anthony from Influx Data. Do you have to train a model for all of the n squared combinations of features? Is that how SHAP works? Did I misunderstand
technically what it does is it kind of trains a model for every single combination of features, like the featureless model, every feature individually, every combination of two features up until like 2 to the n different models. So if you're doing that and you have more than a couple of features, that is an incredible number of models to train, and that will, it would frankly explode my laptop, so I don't think it would handle it. But that's what the TreeShap really comes in handy for. Now there are even faster implementations now, I think, that haven't quite made it into our packages yet, but different, like FastShap, I think is another implementation, or Fast TreeShap. They have better algorithms for approximating these results. Oh, I did mention not wanting to have gender as a feature. Why is that? That's a hypothetical situation. Maybe you're in a situation where, there's, I don't know, something legal going on, and you want to make sure that you're not discriminating against, women or against men in it. So, if you use, gender in your model, and that is affecting your decisions, then with a black box model, you don't really know to what extent gender is affecting the results. With explainable AI, you can look and see, well, we're including gender, but it doesn't have much an effect. And that can help satisfy legal requirements if that comes to pass.
Cool. We got time for about one more quick question. We got about 30 seconds left. Is there anybody else in the chat? Anybody? And so I guess one quick data question is, what was the definition of a readmission? Was it a readmission at UH or a readmission anywhere? And how did you know?
Nick, do you want to take this one?
Yeah, I can. So we are using an UH data set. So the readmission is any readmission in the UH environment.
Super, thank you. And that's the beep. Again, terrific Terrific talk. Everybody give him a round of applause, either real or virtual, whatever you can do. So thank you so much. That was fantastic.
Yep.
Next up is Adam from Influx Data.
Hey there, now my mic's on. Let me just get my screen shared and we'll jump right in.
Awesome, whenever you're ready.
Okay. All right, well, thanks for having me here today. So yeah, so this title is a little bit obscure. I always joke when I interview people for my team, we're called the compute team, which is like, I mean, isn't that what we're all doing? But what my team actually works on is making sure that there is enough compute available to do some pretty large workloads. So that's a really high level context. But before we get into the meat, just a little bit about Influx and about me. So Influx Data is a time series database company. The best way to explain time series data that I have is that combining measurements plus time leads you to taking actions, right? And we see this in a lot of different ways, right? We say, oh well, it's not just that the price of Bitcoin is high; it's how high is it rising, right? Does it look like it's coming to a peak, or so on and so forth? They're looking at the temperature of a machine in a factory, and it's like, wow, this is getting hotter and hotter. Something's going on, right? And so it's seeing those trends over time that lead us to taking action. And so that's kind of the value we're getting out of it. Our database is purpose built. That means that we're not really using off-the-shelf components, but we actually wrote all the code ourselves in Go. And our current product is our Cloud 2.0 platform. That's what I'll be talking a lot about today. This is actually a database as a service, pay-as-you-go model type platform, which is pretty interesting for a database. And our key customer that has emerged is actually application developers. So a lot of people think about time series data like, oh, I'm going to get a Grafana dashboard. I'm going to create charts and get them into spreadsheets and PowerPoints and put things on the wall and get this into the hands of analysts. That's certainly still a use case for our platform, but we have found that in this new generation of analytics, Internet of Things is a huge market area. They want to put all their effort into their hardware, their devices, right? And they don't necessarily have an equivalent budget for the application that drives that hardware. And so it's become a really high value proposition that most of the data coming out of an IoT device is time series data. It fits well into our platform, and the features we provide them cut down their development time. So a little bit about me. I got my PhD in computer science at the University of Maryland, Baltimore County, 2009. Big news this year for UMBC is they actually just got listed as an R1 research institution after just 50 years of existing as a university. That's a really huge accomplishment. I thought that was pretty cool to hear a couple of weeks ago. I left UMBC and spent a few years as an assistant professor at Baldwin Wallace University over by the airport. And in that time, I actually came to my first Cleveland Big Data Meetup in 2013. So 9 years ago, probably a little bit more. And I saw a presentation from a company called GraphSQL. They're now called TigerGraph. And that got me out of academia. I caught the bug. So, that's Doug and I were talking a little bit before all this started that that's a big part of this group. It's really good networking. It's a great way to meet people. There's a lot more tech in Cleveland than I ever realized until I came to this group. So I always try to take the opportunity when Doug calls me for a talk. So I left GraphSQL in 2017. I've been at Influx Data for almost 5 years now. Couple of years as an engineer. In 2019, I took over as the manager for the compute team, and that's where I've been since. Okay, so multi-tenant database as a service, DAAS. We talk a lot about software as a service, and a lot of the software we use is software SaaS. Salesforce kind of being the original players in that market, right? or at least the ones that broke through. And the whole idea is that you don't have to install anything, right? You just go to a website, use the software, setup. Maybe you don't even have to like buy a box wrapped with shrink wrap. You just give them your credit card number, you pay a monthly fee, you got your software, right? It's the prevailing model in software delivery these days. And that's starting to now be true for enterprise customers as well. Used to be you're an enterprise customer, everything's on-prem, right? You gotta own your data. It needs to be in your house. You need to be completely responsible for it, everything else. That seems to be softening a little bit. Databases are really expensive. They're really hard to size, predict what you need. Sometimes you go through all the trouble of installing something and then you reorg a department and you just bought a license for a thing that no one wants anymore, right? So many things happen. So this database as a service model, especially in the age of, nobody actually has servers anymore. So actually none of their data is in their house, right? On-prem just means it's on AWS servers I control, right? So it's a pretty small hop to say, hey, let's do database as a service too. So I had to laugh because I didn't really think about this phrase until I was practicing and said it out loud, but we are the ass behind the ass, right? So what I mean here is that software as a service platforms use us as the back end, right? And so if they're promising 5 nines, we've got to have at least 6 nines, right? And even more. I have a story about a customer who opened a support ticket and said we had 8 failed queries yesterday. We said, well, you ran 10 million queries. And they said, yeah, and 8 of them failed. That was a bit of an extreme scenario, but we certainly get a lot of pressure to say, even a couple of failures here and there, they measure and they see that, and that impact kind of has an exponential impact, right? 1 failure for us might be 1,000 failures for them. And so, another side effect of this is that, our performance in terms of responding to queries has to be a good margin below kind of the industry average. They say like, oh, latency, page load has to be 250 milliseconds or something, right? And so, we have to be in like the sub 50 range for most of our hits, or else we're eating up that customer's latency and they can't use us. And the other thing, and this is kind of related to the availability, a security breach can have an exponential impact, right? One company's database gets hacked and that's a bad day for that company. Our database gets hacked, that's a bad day for every customer we have. So another side of this coin of kind of this multi-tenancy is this idea of tenant isolation. And one of the ways I talk about this with customers is that, the database to an application developer, to an engineer is like really sacred, right? Like that is like the heart of what your company's doing. Without your data, you don't really have any value necessarily. And so we have found that tenant isolation is kind of a really strong unwritten feature for database as a service. So the way I define it for our application area is that you have functional equivalence to a single tenant installation. Or to put it informally, you want to feel like you're the only one using that database. So in terms of compute, that means that you get all the compute that we promised you. We said you're going to get 8 CPUs and you're going to get this much throughput. If I try to use that, it better be available. The kind of secret sauce for us is that, well, if you're not using it, maybe we'll let this guy use it over here, right, and smooth out the peaks that way. But if you need it, it better be there, right? And so we have to keep that promise. The data isolation is a little more obvious and also a little more straightforward. A tenant should only be able to access their own data and nobody else's. It was designed from the ground up to work that way. Privacy is a little bit of an interesting one. No tenant can know what another is doing, right? So we have to kind of have concerns of maybe 2 rival companies knowing that they're both in the same region, and one not causing trouble for the other and being getting any kind of accusations flying across our desk, right? So Those three things kind of go together into isolation, and these are things that we think about for all of the components of our system: storage, query, etc. There's also some physical versus logical concepts that I think a lot about. And there's usually a spectrum of design here for these different dimensions, and there's probably more dimensions than this, right? So in terms of data isolation, are you going to have one database for everybody? That's really inefficient. If you've done this kind of thing before, you end up with a lot of wasted disk space, and we know EBS is expensive, right? Or do we co-locate the data and authorize row by row? Now that makes it a lot harder. Now we're talking about risks of privacy, risks of data leaks. So we have to have a really solid authorization system if things are going to be shared. Can we share a service? Can two tenants execute in the same runtime? What if one of them takes up all the RAM? What if one of them does some kind of denial of service thing, or locks the pod into an infinite loop, or causes a crash, or or could there be some kind of leakage in RAM? There's all these concerns about running two things in the same runtime, even though that'd be a really nice way to share CPU and so on. And then request isolation as well. And that's really the idea that if I submit a request, it should always be kind of satisfied. It should be independent of all the other requests that are going on. I can't say like, oh, AT&T is more important than this other customer over here, so AT&T is going to get their data. If we want to show AT&T favor, we need to do a special case for them, right? That's kind of the core of a core concept that we pay attention to. All right, so that's kind of the preliminary, just setting the tone for things. What I wanted to talk a little bit about today is sharing a query platform. So one thing the compute team does is we don't actually run our query engine, which is the language and the thing that's pulling data out of the database and doing the joins and the filtering and all that. We don't actually own that, but we own the thing that runs the query engine. And we have to make sure that there's enough query engines available to handle all of our customers' workload collectively. And so there's a lot of different ways that this could be done. Some of this is based on experience, some of this is based on research. And so this first one, that I want to talk about is kind of a traditional model. Snowflake has done this. I think some other database companies have done this. VoltDB comes to mind. And the idea is that each tenant comes in and there's a large shared storage. So this is where you start being able to share disks, and you could scale this horizontally, and really, handle replication and backups. And this can be like a really, really sophisticated storage engine down here. So that's the shared part. Then up here at the compute layer, the query layer, there is no sharing at all, right? Snowflake's model, at least, I haven't seen their model in a few years, so forgive me if I'm speaking incorrectly about how they are now. But in their earlier days, they said, well, if you want whatever size AWS instance, we're gonna sell you that instance, times some greater than one factor to cover the cost of our software, and that's what you pay for. If you want a bigger instance, you pay more money, get a bigger instance. You want 2 instances, pay for 2. And if they're on, you're paying for them. If you're off, you're not paying for them, right? It's just very direct data warehouse model. And so what they have observed, and I think a lot of other companies have observed this too, is that when customers start to take on work, like this is the ideal, right? That they've got one query engine just totally utilized. They have another query engine that's mostly utilized. If they have a spike, there's a little bit of space here, right, to absorb that blow. And like on a good day, this is how it works for everybody. But there's kind of some edge cases where this becomes frustrating for tenants, right? Like here, this tenant ordered 3 query engines. Maybe they thought they needed it. Maybe at one time they did. Right now, they could fit all their work into 2 engines, right? And so, maybe they want to downsize or something, right? And so we have to be mindful of that. And then this last one, right? They got 1 engine and they're all full. And unless they act quickly, they may start dropping requests, right? Because they're overloaded on this query engine 1, and there's not anything they can do about it unless they go in there, right? And so that's when companies start offering things like, okay, we'll do auto scaling. If you need another pod, we'll give you another pod. So what does that mean for this customer? Well, they're going to go get a whole nother query engine, and they're paying for a whole query engine to run 5 more queries, because they're on that edge, right? And so how do you kind of resolve that? The other thing that we look at from the business side of things is all this empty space, right? So, depending on how you bill your customers, or even if you bill them fairly and it's fair for everybody around, this is compute that, like, if I could somehow spare it, I could sell that to somebody else, right? And same thing here and here. So I have enough spare compute in theory to supply an entire extra query engine. And so, the margins on this are not favorable. The outcomes for the tenant are not great, because they might say, well, I'm only paying for 1 3/4 servers. I'm only using 1 3/4. Why am I paying for 2? They want what's called micro billing, right? And so these kind of things start coming up. And so then you start saying, well, all right, let's share. And so you go ahead and you build something like this. You have a shared executor, and you start feeding requests into this, and you'll probably have a queue or something in here. If you get too many requests all at once, you don't just want to drop them, right? So you'll fill up this queue, and depending on how many engines you have running in here in parallel, you burn down this queue and everything's great until you get so much work that this thing can't keep up. And if we can't resolve queries, we can't make money. So what are we going to do? We're going to horizontally scale. We're going to put in a load balancer, and we will add another executor and another executor. And so this starts to have some nice properties, right? We can share, and we can see, oh, we're going to start filling up work, and everything's getting spread out nicely. We're at 100% utilization. And this was actually the approach we took a few years ago when we initially created our cloud platform. It seemed to kind of check all the boxes of, okay, we can scale, but we can share. But then we started seeing some really strange behavior. Not strange behavior, but behavior that our customers didn't like. All right, so right now, all our executors are full. And so a new request comes in, load balancer, let's say it's round robin, random assignment, whatever it is, just let Nginx do the load balancing. That's really not an important part here. It decides, okay, these are all equal, so I'm going to send this guy over here, right? And so he's happily waiting. He loves our platform. He's waiting. And then queries start finishing up. So in the worst case, we'll see something like this, where these queries start dropping off, and oh no, on that pod over there, there's all these really long queries. Some customer came in, they ran 3 queries in a row, and they're each taking like 2.5 minutes, right? And so this guy's got to sit here and wait 2.5 minutes, and now he's sad. He's not liking our platform because it's a 1-second query, and here he is waiting 2 minutes for a response. All right, he's like, I didn't ask for that much data. Why is it taking so long?
Adam, quick time check. You got 2 minutes left.
Oh, wow. All right. Well, I've got just a couple slides. All right. So the other thing is that if that pod goes down, all the queries go down with it, right? So this kind of breaks the whole multi-tenancy privacy type thing, right? All right. So here's the one we're actually doing. So since I have 2 minutes, I'll probably just skip to this. So what we did is we took the queue out of each execution engine and made one big global queue. And what this lets us do is that when this new guy comes in, when a pod comes up free, they can go do their work right away. Right. And so I think the big takeaway lesson here is that kind of how you design, just not how the work happens, but how it gets organized, how it gets allocated, just the concepts of where and when things stand in line can have a really big impact on your customer's experience. The other thing that happens, that guy over there runs a bad query, it only takes them down. Doesn't take down our happy customer here. I'm going to skip this one, but for measuring throughput is really simple in this platform. It's just kind of a ratio of how many pods are occupied. this is our architecture. We implemented everything in Kubernetes, and we actually have multiple queues, and we can have multiple pools of workers. This lets us do things like have different sizes and to create different levels of isolation for customers or for our applications. Like we have an automated task system. We also have an ad hoc real-time query API. So we actually serve those out of 2 different lists, right? And so just a lot of flexibility with this model. And the nice thing is that all these components are just reusable off the shelf now. So there's no new code to write. This is all systems level work and routing work at this point. And in case anyone's wondering, we could do like a production workload with just a few hundred pods, right? So we see kind of at 600 queries per second daily average that goes up and down. And so we see peaks of like 1,500 to 2,000 queries per second occasionally. So 300 pods is a lot, but it's not like insane in terms of Kubernetes life. And those are all identical pods, so they're pretty easy to manage. All right, I think that's it. I can just skip this last slide unless there's questions about it.
We got time for one quick question. Adam, do you have any contact info for folks that have follow-up questions? How do you want to handle that?
I should have put something on my slides. I'll send you something.
Okay, cool. I can post it on the meetup. So Adam, thank you so much. And again, thank you for mentioning the Cleveland Big Data connection. I think it's a fantastic story, and I love it when stuff like that happens. People meet, make connections, new interests, potentially new gigs. So yeah, that's so great. Thank you. Everybody give Adam a round of applause, both real or virtual. And then next up is Arista, who is a longtime friend of the show. Arista has done multiple talks over the years. And Chris, you ready? Whenever you're ready.
I am. Thanks, Doug. Let me just get my own little timer going here. So I try to make sure I beat the Doug timer. It's been a little while for me since I participated in one of the big data meetups. I forgot about the timer. I love it. I miss it. I need to adopt that in some of my other presentations. So let's see here. I'll share the screen. Put it in presentation mode. So just to check, want to make sure everybody can see the screen.
Yep, I can see it.
Cool. All right. Arista. So for us, what we wanted to speak about tonight is really tap aggregation, or what some people say would be network packet brokers. So less about the core routing and switching elements and more about, hey, there's all these fancy tools. There's a lot of requirements or requests for visibility. How do we take what we see flying by on our wires at 19 billion packets per second? How do we make that usable for people to do data analysis, or security-minded folks to want to see what's going on the wires? So a few years ago, started giving this presentation at meetups that were really outside maybe just network engineering audiences. And one of my sales folks came up with packets in purgatory is a way to kind of describe, what happens with this data here. And I've got my contact information here, and we've got a few of the Arista team also in attendance. So I think Chuck and Jeff, if they could put their contact information in the chat for anybody that's interested. Talk about Arista a little bit, but I'd rather focus on just the industry and more about vendor agnostic solutions and just looking at what problems specifically are we trying to solve. So current state networking, just to bring everybody up to speed, we saw a ton of 400 gig get purchased last year. And the industry knew there would be an uptake in 400 gig. We expected that demand from the internet service providers and the cloud service providers. So folks like the public cloud, the predominant public clouds that you're aware of, but also folks that are help with data center or hosting, teams like Equinix and others that provide on-ramps so that you can get to consume your services in a public cloud environment. What really caught us by surprise is how much 400 gig was purchased by what we would deem enterprise. And it was more of your average networking team, if you will. So we saw a huge ramp up in per port quantity and per port purchase of 400 gig in the general global addressable market beyond just those cloud service providers. And it drives a lot of the ancillary things that we need to do, like visibility tools for folks. So, why so much 400 gig? Well, down at the compute layer, your databases, your physical, endpoints that are connecting into the data center network infrastructure, those speeds are increasing. So we've gone from 1 gig to 10 gig, 25 gig is most common now, but we're starting to see 50 gig, 200 gig, or excuse me, 100 gig and even 200 gig at the edge of the networks. And because we have so many assets that are connecting at those speeds, we need to be mindful of oversubscription ratios in our backbones, whether that's your data center backbone or maybe your corporate wide area network, or even the service providers or the internet service providers. They need to stay ahead of that demand. And that really drove the 400 gig adoption. We're also seeing less space required to deliver these kinds of speeds. So just a few years ago, it would take an entire rack of equipment in order to be able to drive the bandwidth that folks were asking for. We'd have these huge oversubscribed systems where we're trying to show you a 25 gig port, a 50 gig port, or a 100 gig port. That's been really crunched down now to where we can deliver like 32 ports of 400 gig in just one rack unit. So considerably less space, considerably less power, and really lower CapEx and OpEx because you're buying fewer devices and fewer optics. With that reduction in space, we also are very mindful of the amount of power that we're requesting from the data centers. So if we get too power hungry in 100 gig or 400 gig, that of course is going to drive up your facilities cost for things like the power to power the devices, whether that's AC or DC, but also with the cooling. And then additionally, with these higher density chips that are out now for us that we're putting in the network equipment, we're actually seeing a reduction in the cost per port. This is a rare triangle of things that are all coming together here with 400 gig. And we're going to see this with 800 gig. And similarly, we're going to see this with 1.6 terabit interfaces that will be out later in the decade. But it's seldom that we get the opportunity of to see, hey, it's a lower cost, lower density requirements, lower space, power, and cooling. And what's driving these bandwidth demands? Well, here we're talking about big data. AI has found its way outside of the research labs. I just recently came across an article just last week. A data center group released an article about all the individual verticals that now are requiring AI for just either to survive as a business or to try to leverage as a business differentiator. So, we had certainly seen that with large organizations working with teams at Meta or at Google or Apple that were driving decisions based off of the outcomes they were seeing in AI. Teams, even, the old Explorers days or the Watson Health days. But now that's actually being shifted to everybody. We're seeing it in the logistics groups with folks running shipping, which we're all suffering from horrifically today, trying to get equipment to each other to build these infrastructures. So it isn't just the largest organizations that have a need for some of these environments. We're seeing them in the smaller verticals as well. And there's a lot of characteristics once you start introducing these kinds of workloads to the networking infrastructure, where as a network engineer, while we certainly don't operate these applications and we don't own these databases, we are responsible for building the appropriate roads for you so that you can get that data through. And paying attention to what's going on in a converged environment where we used to be able to do things separately, like let's say maybe fiber channel or InfiniBand. We're seeing all this come together on Ethernet. So from a network engineer's standpoint, Ethernet and IP have pretty much won out the day. Like gone are the days of all kinds of different transport technologies, gone are the days of different kind of interface media. And now that we're adding, converging more here, we're seeing a need to make sure the network is robust enough to be able to accommodate all that convergence. So we actually have customers now that are asking us to build dedicated AI networking infrastructures, just because there is so much data here with sensitive requirements. And we want to be careful of how we handle competing with just your average daily workloads, if you will. Something that's coming at us now as we're seeing a lot more requests for Rocky V2 because of RDMA adoption. So the fast, low latency, high bandwidth consumption of RDMA. Initially, we saw that a lot with being serviced by folks at maybe InfiniBand or dedicated OEM environments. We're now converging that into the routing and switching infrastructure with things like quality of service to help us with explicit congestion notification, data center bridging, and technologies that previously were separate, but are now mixed into the network. So I laid that as groundwork, hey, what is driving the bandwidth demand? What is all this data? And then now we get into, well, who's interested in looking at this data? So when we think about everything is getting written to a wire, that wire now becomes an asset that we can use to do things like monitor application performance, or maybe we can hand metadata of that traffic that we're seeing on the wires. We can give it to our security teams that are very interested in seeing, every packet everywhere in the data center to either catch real-time security problems, or perhaps to be able to go back to a moment in time. Whoops, we realized we had some sort of vulnerability or an exploit that someone was able to take advantage of, but we find out 35 days later, 50 days later. How could we go back and actually perform forensics on that exploit? So just to help you, with some of the naming, TAP aggregation, network packet broker, some other light bulb moments, people may describe these as network time machines or DVR for your network, running packet captures, sniffers is a common tool that you'll hear in association with this, as well as things like Wireshark to be able to analyze the conversations that are occurring between these endpoints. So when we're building data centers right now, what we found ourselves doing is we're really building 3 networks. So if somebody comes to us and says, I have a brownfield environment I need to refresh, or maybe you're building brand new, it's not just the data center networking that we now have to pay attention to because of COVID and all the remote work. We need to make sure we're taking our out of band access seriously. How can we get in when there's moments of degraded service or outages? But we're also building this visibility network. Everybody wants to analyze what's going on from a security perspective, or like in this case, hey, somebody's complaining it's taking too long to get an answer to this database query. Well, where is the problem? Is the problem with the database in and of itself? Is the problem with the network? Is the problem with how the query was written? And these types of tools, network packet brokers, they save that data for us so we can go in and analyze and pinpoint exactly who to yell at. Do I go and yell at the network team, or do I call out the DBAs and let them know we've got some query issues? So where these things get plugged in, on the left here, this is the production routing and switching network. This is where your compute, your databases, all that stuff's connecting. What we're going to do is we're going to take regular switches and we're going to lobotomize them. We're going to tell them, hey, we don't want you to route and switch anymore. Instead, what we want to do is we want to use you to make a copy, right? A Xerox copy of each and every packet. And then we want you to feed that to tools. So we have an environment here that takes advantage of flow information, and we direct a copy, so a non-production copy of your traffic, and we send it to these various tools. Well, that's an application performance management tool, or lately, Well, with the focus on security so much over the past year, 18 months, there's just a flood of security tools that people are adding to their network. So it's common for cybersecurity folks or InfoSec folks to come to a network engineer and say, hey, I've bought this nice shiny new tool, and I need you to feed all the production packets to that tool. And so that's where this need arises, where we can't plug 100 of these tools into the production network. We have to keep in mind the production network's core job is to reliably move data as absolutely as fast as possible. And for us, fast could mean 4 nanoseconds from port to port. So from ingress into the switch to egressing that switch, or as high as just 2 or 3 milliseconds. The network equipment just wants to get it in, analyze it, get it up, and get it out and on to its destination as fast as possible. But while we're doing that, what we're going to do here with the network packet broker is we're going to make a copy of it. We're going to Xerox it, and as many copies as we need to make to feed all of these tools so that you guys can perform the analysis on them to verify performance or security issues. And part of this, there are additional tools you'll see from Arista, from other vendors, where it's not just enough to feed these tools. Sometimes we need to go back in time. So this is more the DVR element of a network packet broker. And that I made copies of this data and I've written that off to disk somewhere. So you'll often hear about like a recorder node where we can store all this traffic with goals of maybe 3 days of retention. The goal could be, maybe a NERC SIP environment or SCADA environment where, hey, we've got a mandate to hold on to all of this data for at least a year. So we've got these compute elements that we can add to our network packet broker solution where you can save off all that data and it can scale out. So not only in just one 192 terabit node, but hey, I can create a cluster, or if I need to, I can even extend that further and leverage some storage you have through NFS and attach to it to be able to write off this traffic for later analysis. And we're feeding all kinds of information here. So we have the raw packets that are going to the tools to be analyzed, but we also have flow data, like our sampled flow or what's called S-flow, some proprietary solutions that are out there in the industry like NetFlow or JFlow. But what we're doing is we're asking the network, hey, while you're seeing all this stuff go flying by, could you grab just a little bit of the information about that and feed it to these tools for analytics on performance? And oftentimes those are third-party tools. And then also, hey, I need to actually troubleshoot a problem. So, thinking about a workflow when someone brings an issue to me, whether it's Adam or Doug calls and says, hey, we're seeing some sort of performance problem. We need you to dig in and verify whether it's the network or not. We know it's not the network, but sometimes I need proof, right? If I'm not guilty, who is? So who am I going to help Doug or Adam yell at? And so we'll actually leverage these nodes to do some analytics for us, where we can go grab the raw traffic that flew by 5 days ago, 6 days ago, and run some analysis on that and actually be able to look at the raw packet capture, the actual real data. So a quick story as an example, as a network engineer, I vividly recall a group of application owners coming and yelling at the network team that there was a performance problem. And we started to dig into the issue and we were looking at the load balancers. Nope, those look fine. We were looking at the front end compute. Now that seems to be flowing just fine. And then we got to looking at the conversations between that compute and the databases, and we realized, oh, this packet went in, but it was like 43 seconds later before we saw a response come out, right? So now that we have this raw conversational data, we can look and see, well, the network handed it over pretty quickly, the compute handed it over pretty quickly, but it got stuck over here. And with the raw packets, we were able to go to the DBAs and say, well, this is the query that was run. This is what we saw go into the system. And immediately, right away, 3 or 4 DBAs spoke up and like, what the hell kind of query is that? Of course, no wonder why it's taking so long. That's bad. They should have ran a query like that for a data set that they were asking for. So that's the kind of information we can get. That's what we mean by visibility where it's not just about being able to look at things real time right now per millisecond or even per nanosecond, but being able to dial back days, weeks, or even months, depending on the need. And putting all that in context, where is the problem? What are all of our devices? Someone mentioned IoT. We have all these individual endpoints that are coming in, and quite frankly, a lot of those endpoints are very, very dumb. They're very stupid. They don't have a lot of the networking tools built into them that we're accustomed to leverage to help troubleshoot and verify performance. So a network packet broker infrastructure like this would then give us that visibility and help us be able to pinpoint, yes, this is a network issue, or no, this is actually a DNS issue, not network transport in and of itself. So with tools like this, we can go in, run the analytics, run the recorder node, be able to query and access those packets, and be able to even replay the scenario. So we can pick this up, and just like the comparison to a DVR, it could be a week or two later, and my security team could replay the conversation. They could see these packets flow again to get an idea of what was happening here. What was the east-west or lateral movement that a malicious actor was using in the case of a security situation versus an application performance one. And then just also looking for other things like, hey, we have all this visibility, why don't we baseline it? And then we could notify each other or individual groups based off of anomalies or deviations that we see out of the baseline, at least from the myopic view of a network engineer, what we're seeing written to the network and how it's performing. So just about a minute or so left before Doug gets at me with this timer. Hey, parting thoughts, for us is help your network engineers build what they need in order to feed what you're asking for. A lot of times, somebody will have a great new shiny tool they'll bring along, but if the network team wasn't included in that decision or design process, we might not have the tooling that we need in order to be able to feed your new products. Certainly be a student of the industry. Meetups like this are fantastic. I love that Doug has this, and there's a lot of other ones around the state that are wonderful. I learn a lot from. And then always ask those second level questions. Okay, if we buy this, then what would happen? If we have this expectation, or if we release this feature, what dominoes could fall, right? So thinking about some of the adjacencies or the ancillary items around each one of our technology areas, and just kind of getting outside of our own silos and thinking about the impact to one another. And with that, Doug, I'll say thanks, and I appreciate the airtime.
Oh, thank you, Chris. That was awesome. That was just amazing. We've got a little bit of time left here, like 30 seconds. Anybody, quick questions from folks? Anyone? How might here's a hypothetical, but not hypothetical, is a number of the intrusion stories that you see in the that have been in the news is somebody gets access to a data, to a network, then into a data source, extracts data, encrypts it to, what I mean, and then extracts the encrypted file. Like, how can this still pick up on that anomaly? Does that make sense?
Oh, it does. Absolutely. Yeah. You start getting into those InfoSec topics like network detection and response, because the key here is that all that stuff gets written to a wire. So no matter how somebody exploits something, I mean, it's very rarely that somebody's coming in with a thumb drive and plugging into something to steal it. They're remote, right? The attackers are global. So they have to, whatever they're doing has to be written to a wire, and it's okay if it's encrypted. We don't need to decrypt that in order to be able to sense something is wrong. So by feeding these tools and looking for those anomalies, or just being able to play back and realize, hey, why did this IP camera in this pharmacy start calling home to, name XYZ evil country, right? Or country state actor, political actor. We don't know necessarily what exactly was exfiltrated, but we can see that there should have never been communication from this device to that destination. So tools like this giving us the visibility to pick up on that, either in real time, notifying us something that this is way offline, like we've never seen this thing call home out of country. There's just something wrong here, right? To take it back to like the recent SolarWinds outage, or excuse me, exploit. Hey, why all of a sudden are we writing? Why is my SolarWinds writing
Yep,
to
yep.
Russia, as an example? So these are absolutely helpful, and we aren't necessarily as a network team doing that analysis, but we're saving those packets that normally we just fly through a device quickly. We're
Exactly.
saving that off so that you can query and determine that stuff at another time.
I'm gonna I just want to go an extra 2 minutes on this, just simply because there's been so many security topics that have been come up recently. Like, what's the in terms of look back, in terms of that DVR size, like how does one size for that? Because you're literally capturing like everything. I mean, like it's mind blowing of like to think that that's even possible. You know what I mean?
Yeah, it is. And it is an exercise to try to figure out, okay, what do we need to include? Or maybe sometimes for people, the exercise might be easier to determine what we're going to exclude. So to say, maybe perhaps we don't need to copy all the backup traffic. We've already got the originals, right? So if somebody's doing backups, maybe I don't need to copy that off. So I'm going to make sure I exclude that. So we can pinpoint, really starting with the crown jewels. What do we know for sure that we need to hold on to? What PII information, what PCI or HIPAA, or whatever realm you're under. Are there any mandates to say you have to hold on to this data? When I think about NERC, SIP, and SCADA environments, we're looking at PLC data that we need to hold on to a year is the requirement. So if we can get granular enough, what you can do with these tools is say, hey, specifically, it's just identified data from these devices to these devices, we'll save that. And usually we start there. And then we just open it up. Yeah, we want more. We want more. Everybody
Okay.
else see more data. So you just crank it up, and that gets you an idea of what you need from a storage standpoint for as long as you'd like to have it from a retention.
That's really cool. Does anybody else have another one more question? And Chris, you've got your contact information. I see Chuck put his contact information there. So if anybody else has any other questions on this topic, contact Chuck or Chris. I know you had your email address in the slides earlier. So again, thanks everybody. It's fantastic talks. It's crazy how all this stuff is related. I mean, we started with an AI related talk, not an AI related, an AI talk in the first one, and then you ended it with a networking talk that was impacted by AI use cases. So it's all of this is interrelated. So yeah, great stuff. Thanks everybody. And then we'll meet again in May. And if anybody has any other topics they'd like to hear, hit me up. And if anyone would like to be a speaker and friend of the show, also hit me up on Meetup. Always looking for new talent and new topics. So thanks everybody. Have a good night.